Okay, welcome back to our machine design series. In this video, we're going to dive into the fundamentals of the design process, key considerations that every engineer needs to keep in mind when designing a machine. So from understanding how the design process unfolds to professional responsibilities, factors of safety, this lecture is going to set our foundation for the rest of this course. So let's get started. Now, the first thing we need to do is lay out the phases of the design process. And as we said in the last video, design is an iterative process, meaning that we don't just go from start to finish in a straight line. Instead, we move through these different phases, refining our work at each step. So the first phase is identifying a need. And for purposes of this video, we're going to use the example of office furniture. There's a demand for office furniture that enhances productivity and supports employee well-being while also aligning with modern office aesthetics and budget constraints. So that's our initial need that we have identified. Next, let's define our problem. So in defining the problem, we pick out the aspects of design that we need to optimize for. So we need to design a chair that is ergonomic, stylish, and durable, enough to last 10 plus years, with materials and construction methods that keep it affordable for most businesses. So see how the difference between the identification of the need and the definition of the problem steps is really in the way that we're defining the variables and the function parameters of our design, what we're aiming to optimize or improve. And then, as we said at the beginning, this is an iterative process. So through defining your problem, you may re-identify a new need or a different need that you didn't identify initially and add that to the definition of your problem. Okay, and then once you're satisfied with the need that you've identified and the problem you've defined, then we can move on to synthesis. And in the synthesis step, we're going to develop multiple design concepts for our product, in this case, an office chair, considering different materials, structural configurations, and different aesthetic styles. And again, we can iterate here, returning to redefine our problem or re-identifying our need and iterating through as many times as we need until we're satisfied with these first three phases. Then we'll move on to analysis and optimization. And in this step, we're going to evaluate the proposed designs that we came up with in the synthesis step. We can evaluate them through stress analysis, ergonomic testing, cost assessments, and many other types of analyses and optimization. We will select the most suitable materials that we can identify and refine the structure for increased durability, and our aim will be to balance cost with comfort and style. Okay, and then we continue to iterate as needed. And once we're satisfied, we move on to the evaluation step. In this step, we're going to prototype the one design that we've identified as being the optimal, and then we'll use that prototype to conduct user testing, assessing the aspects of our problem that we identified in the earlier steps. So asking users to rate the chair based on comfort, durability, aesthetic appeal, and then collecting feedback to determine if the design meets identified need and satisfaction of the problem definition. So this is not just user testing, but you can also evaluate designs through mechanical testing and other forms of evaluation. And then finally, once you've iterated and your evaluation has passed the necessary tests, then you move on to presentation of your design. And this is sometimes an undervalued aspect of an engineering education, in my opinion. Presentation is really about selling your product, and this, in my experience, is how you get promotions, is being a good presenter and really communicating well with all different teams across the organization that you work within. So learning how to have good presentation skills is a great tool for your engineering toolbox. All right, and throughout these phases, you should also be communicating and interacting with not just other engineers and manufacturers, but also potential customers, regulatory bodies, your sales team, management. Good communication is essential to have a successful design. All right. And then next, let's talk about computer-aided engineering. Today, we rarely design anything by hand alone. So computer-aided engineering tools assist us in modeling, analyzing, and refining designs efficiently. So we can break down this overarching term into computer-aided design. And those are things like SolidWorks, Creo, Autodesk, tools that allow us to build 3D geometries. Then we have our analysis tools, and these we can break down further into engineering-based analysis tools and non-engineering specific analysis tools. So on the non-engineering specific side, we have things like math solvers, which some examples of that are Maple, MathCAD, MATLAB, things that are not used exclusively by engineers, but can solve mathematical problems for you. Then we have word processors, of course, things like Microsoft Word, and we have spreadsheets, which is things like Microsoft Excel. Then on the engineering-based side, we have tools that perform more engineering-focused functions like multi-body simulations. This is things like MSD Atoms, Virtual Lab Motion, Working Model. These are tools that help you simulate rigid bodies and dynamic situations. Then we have finite element analysis, which are tools like Abacus, MSD Nastran, and ANSYS. So these tools help you analyze the way that bodies or objects deform under different loads and so much more. And then there's computational fluid dynamics, which are tools like CFD++, STAR CCM+, and ANSYS Fluent. So this is a similar tool to FEA, but focused for fluids rather than for solids, which is what FEA is used for. All right, but no matter what tool you use, do not forget that if you put garbage into these tools, you will get garbage out. So do not always believe what you see when you perform an analysis like this. You have to make sure that it makes sense with your engineering intuition, that you validate your analysis results with other simpler examples, but similar examples that you can check by hand. But using these tools effectively will help you minimize errors, reduce your development time, and improve your overall design performance. So they can be really useful, but we have to use them carefully. All right, now, one part of using these tools carefully is acquiring good technical information. So this can come from many places, including libraries, government sources, professional sources, vendors, the internet. So as far as the internet goes, you can find a lot of different things on the internet. You have to make sure that you're using websites that have been verified and are mostly in common use in the industry. So thomasnet.com is one example of that. And finally, just a note on AI. You need to always be very careful when using AI. The AIs will tell you this themselves if you ask. You need to double check any information that's been generated from an AI. And then here's just one example of a mistake that AI could make. It might tell you that this thing that clearly looks like a cat is a dog. And if you don't double check the AI, then, smaller errors can wind up becoming really big errors in the end. So Bad data leads to bad design, so always verify your sources. All right, as engineers, we have ethical and professional responsibilities to be competent, responsible, ethical, and professional. And there are many ways that you can accomplish this. One good approach is to be systematic when you're solving your design problems. So understand your problem, identify what you know. I um, there's a professor who I used to work with who would say, you need to know what you don't know. Um, and in these two steps, you need to, again, be communicating with your management, your sales team, your clients, etc. Then we'll identify our unknowns, formulate a solution strategy. So this is where you're going to use tools like charts, free body diagrams, your CAE programs, equations, etc. And then state all of your assumptions and decisions. Keep a record of all of these. Keeping good records is a really good habit to get into. Make clear, why you've made decisions that you've made, and help someone who may come along behind you understand what you had built into your particular analysis and solution. All right, then analyze your problem, of course, evaluate your solution, and present your solution. And again, presenting is a skill that will come in very handy throughout your career. And part of that is knowing your audience and knowing at what level you need to target presenting your information. How technical do you need to be? How salesy do you need to be, etc. And again, communication is key. So make sure you're keeping a journal, practice speaking. Engineers are or should be really go-between for management, for clients, for manufacturing. Um, and it's not just about your technical skills, it's about your integrity, your accountability, um, and your communication. Okay, so on other professional responsibilities, you also have a responsibility to keep current in your field. There are several ways you can do this. One is to join a professional society, ASME and SAE being two notable examples, especially in the field of machine design. You can take graduate classes. So this is a course that's offered at the university that I teach at, called Advanced Solid Mechanics. You can read technical papers. So there are papers that are published, through ASME and SAE. There's many other technical papers, including open source papers that you can read without, paying the cover fee. So all in all, I tell my students, you may be done with your exams soon, but you are not done with learning, not ever as an engineer. All right, then to ensure safety, reliability, interoperability, engineers rely on standards and codes. So let's define first what standards and codes mean. A standard is a set of specifications for parts, materials, or processes intended to achieve uniformity, efficiency, and a specified quality. So one example of that is this ISO 9001, which are the requirements for quality management systems. These standards are often voluntary, but designing to a standard is a good way to ensure that your system will work well with other systems and other machines that engineers have designed all around the world. And then a code is a set of specifications for the analysis, design, manufacture, and construction of something. So an example of that is shown here is the ASME boiler and pressure vessel code, section 9, which defines different specifications for pressure vessels that are built to the ASME code. Now, safety codes do not imply absolute safety. So designing a machine to a specific safety code does not imply that it will be absolutely safe forever. There are many other checks that need to go into place. These are simply, some of the steps that you can take to help create a safe and efficient design that also meets industry standards and requirements. Okay, next, talking about safety, let's talk about factors of safety. We will never design something, a machine or a component, right up to the failure limit. There will always be a margin for safety, and the factor of safety is a parameter that accounts for uncertainties in material properties, loading conditions, and other real-world variability that exists. So the definition of a factor of safety, it's a unitless term. It compares your loss of function parameter to the maximum allowed or predicted value of that parameter. So in equation form, it looks like this. We often denote it with a lowercase n, and it's equal to our loss of function parameter in the numerator, and then our maximum allowed or predicted parameter value in the denominator. And that parameter could be load, stress, deflection, any kind of parameter that we're designing our machine around. So a common example, might be our safety factor for one design may be equal to the ultimate strength of the material that we're using divided by the maximum predicted stress in the material in our particular application. Couple notes on factors of safety. A part can and probably will have multiple safety factors, each one characterizing a potential failure mode. And the failure mode that is most likely is the one with the smallest safety factor. Another note, the choice of safety factor may be dictated by a design code or standard, but most often you are going to need to use engineering judgment to choose a safety factor. Now, how do you choose one? There are many parameters that will typically affect the selection of your safety factor, and I've listed some of those below with the comparison showing you how those parameters typically affect the value of a safety factor. So on the left side here, we're going to have our factor of safety or safety factor, and then we will compare how that changes given different material reliability, different loads and environmental conditions, and then the question of, does weight matter? Do we care how much this structure weighs? Okay, so on the low end, we're talking about safety factors that are between 1 and 1.2. Note that the safety factor always has to be greater than 1, so that's not a less than or equal to sign there, that's less than. And these low-ish safety factors are typically in place when we have high material reliability, when our loads and environmental conditions are not severe, and when weight does matter. So these are things like aerospace applications where having a heavy structure is really not an option. And so what engineers will do is perform a lot of analysis to reduce the uncertainties in the design and have the design still be safe, but with a lower factor of safety because there's a lower range of variability that we can expect. Okay, and then factors of safety can go higher than 5, and this would be in applications where we have a low material reliability. So, either the material doesn't have reported properties for all the aspects of design that we're worried about, or Maybe we're using parts that have been scrapped and we don't know the origin of those parts and we don't have time to test them. Then we would consider our material reliability to be low and we would need to up our factor of safety to account for that variability. Our Lowe's environmental conditions may be severe. So, for example, for a building, especially buildings in places like California where earthquakes are high risk, the environmental conditions on that building can be severe. And so we need to build buildings to a higher factor of safety to account for that variability. And then the question of, does weight matter? If weight does not matter, then typically your factor of safety will be higher, because you can always add more structure, more support to something and have it, I guess, that increases the safety by increasing the strength of your structure. And so then it can handle more variability and more uncertainty that you haven't taken time to analyze. But all of this is generic guidelines, and there are many exceptions to these guidelines. Please do not take this as the final word on safety factors that you implement in your specific application. Make sure you're talking to experts in that particular area before you make any final decisions on the value of your specific safety factor. And there are other considerations that you may need to take into account for your particular design. All right, so that sums it up for this video. Today we covered design process, engineering tools, acquiring good information, professional responsibilities, standards, safety factors, and that's going to be the foundation for much of this course. Next time we will start discussing load and stress analysis, which is crucial for ensuring that designs can handle real-world forces without failure. If you're enjoying this series, please don't forget to like and subscribe, and I will see you in the next one.